and it is Academy of Finland funding, so that's national funding agency for like sort of research related matters. And then we have sort of 5 groups within 4 different institutions in this consortium. So we have Helsinki University, Aalto University, Turku University, and Finnish Meteorological Institute, where there's 2 teams coming from the Helsinki University. So Helsinki University provides a modeling team for the science data, and it also provides an observation team where, let's say, one is more concerned about like actual simulations, and the other one is more concerned about like overall getting more input for their studies. Then, as you know, Aalto University is building the platform, and then 2 instruments are coming from the 2 other institutes. Okay. We will skip this. So, Foresail, and we are starting achronologically, so anti-chronologically, because here was the slide about the Foresail consortium and so on. But like, you will hear later what Foresail 1 is doing. So in Foresail 2, we basically in Helsinki University they are developing this glaciator model. It's like the world-leading magnetosphere modeling for like, and you can produce these kind of also animated flow simulations of like the solar wind impinging on the magnetic field of the Earth, and then creating, let's say, different shock regions and like this turbulent region in here and so on and so on. So you can they are modeling that. And the problem though is that since 2019 there is no more Van Allen probes or cluster mission was also one that was dedicated to that. So basically there is no more probes available. And as you may have also heard, is that we are currently going into a high phase of the sun activity, meaning there is a lot happening concerning this kind of stuff. And the problem is that we don't get like actual data from in situ measurements, because we don't have any proper probes in the correct locations, because all of them have deorbited or have been decommissioned. Okay, and that's sort of the idea. And these are the 4 mission goals that we have. And actually, Foresail 2 is going really with like the requirements definition first, and then developing it from there. You will see that Foresail 1 had a completely different approach, or well, just was a different approach. I'm not judging, but actually I am not. Okay, so the idea is that there are some ultra low frequency waves going around inside the magnetosphere, and they can accelerate or scatter or transport the electrons in the Van Allen belts. Okay. And it's very interesting, because the Van Allen belts, of course, have a huge influence on like satellite lifetime and so on, and like also stuff like that. So the idea is how do these ultra low frequency waves interact with each other, and then sort of what kind of turbulences can there occur, and how do they interact. And then we have 2 sort of technology goals, which one is the Coulomb drag force, and you will see this is a sort of a theme in the Foresail and also in general in the Finnish satellites. This is very much sort of related to the plasma bragg technology that you have heard maybe already a bit, and sort of Foresail 2 would have also or will also sort of try to investigate that. I will tell later basically about what the status of Foresail 2 is. And then, of course, this maybe our own goal is like how, because this mission goes into a GTO orbit, into a geostationary transfer orbit. Is it even possible to do it with a CubeSat with commercial off-the-shelf parts? Which is not clear because all the missions so far have been sort of with like millions of dollars and so on, and like built for this kind of purpose. And yeah, so that's sort of one of the other goals as well. So how is the situation looking like? So the problem is that the ultra low frequency waves are relatively far out. Okay. And together with the EMIX, which is the electron, I can't remember. It's also one of the phenomenons, and as you can see, they are quite much more inwards. So that's why, and the interaction between ULF and EMIC is quite interesting, and that's why the orbit has been chosen to frequently pass both of the regions. Which is then in the case of this mission a GTO. And this brings some interesting challenges with it, because in a sense we are interested in both of the Van Allen belts, so the inner one and the outer one. We have to also fly through them, meaning the actual satellite also has to endure that, of course. All right. So this was the original proposal, and the current status is it will not fly like that. So basically we will do 3D measurements of the magnetic field. You can see here already the magnetometer. We have electron and proton spectrum measurements. On the other side of this image there is a electron and proton telescope detector. And then also on that side there's this puzzle brake tether for the Coulomb drag technology demonstration. And here you can see that the mission lifetime is very, very short. This is actually mostly due to the radiation, and that we don't think that the normal level that you can endure with like commercial off-the-shelf components is around like 10, 12 kilorats. After that, you will see problems. And sort of this is the predicted time that we made, that sort of we wanted to do, like 6 months is also the minimum time that the science wants. And then, and actually we think that we can do it actually for 1 year in the end, so with our solutions that we have thought of. Yes, and the idea maybe is also, so there's a unfortunately now with the current geopolitics a bit stagnating project, but this is part of the COSPAR, sort of endeavor, which is called CORBES. And COSPAR, I don't know, have you heard of COSPAR before? Okay, so COSPAR is one of the leading sort of science organizations across the globe when it comes to space physics and space science and space probes. It's basically they do like big conferences and like bring all the people together, and within that there has been this task force established of like utilizing small satellites for space research more. And the idea would have been, that's why you always see 2 satellites, that we contribute to this kind of endeavor 2 satellites out of 10. So it's a heterogeneous constellation. That was the idea, that sort of, was it, yeah, so basically they are all in the same orbit, but they have like time-wise separation, so that you can get like a very nicely time depending signal, and basically all of them have to have at least a magnetometer and some kind of other instrument. So there's sort of common guidelines where they sort of set in. And the interesting part there is why the geopolitics is a problem. There's US involved, there's Egypt involved, us, and China. And the problem is that sort of all of these players, especially the US, doesn't want to play with all of the others. So yeah, let's see what comes out of this. At the moment it's on hold, unfortunately. Right, mission constraints. So because it's a GTO mission, orbit lifetime can vary a lot. Because actually the orbit lifetime depends on, unfortunately, it depends not only on the day that you're launching, but actually on the hour that you're launching. Meaning that if you have a launch delay, it might be so that you're unable to fulfill the target lifetime in terms of the orbit of, in this case it was 25 years, but if you now go to the 5-year rule. So that's why there has been several constraints about this mission on how to ensure that the satellite is injected into an orbit that is within the regulations. Yeah, so we have made different. So this is basically the orbital lifetime, and basically you see different dates. So spring, summer, autumn, and winter, and you can see that if, depending on the perigee height that you're injecting and also the apogee height that you want, the red means it will not come down within the 25 years. The green means it will come down, and the others, and you can see it varies a lot. And this is not even, and this is not even showing the hourly dependence. So this is really a concern that you have to think of if you're going beyond low Earth orbit, at least Earthbound orbits. Oh, I have a video there. Cool. This presentation has been given a year ago, so I can't remember everything again. So basically, this is how it looks, there is a slight orbit precession also. So if you're looking at the year, the orbit stays the same, but so this is Earth, and this is maybe the apogee. Then it's like moving around like this around the sun. Okay. No. Yeah. So then we came up with sort of the concept of, okay, how do we do this? Because this was just the idea basically, and how do we do this? So we have to go into GTO, and then there are several configurations that you can think of, like how the satellite sort of is the attitude is related to the orbit. And in this case, there is a requirement that the tether needs a spinning spacecraft, and also the particle telescope needs a spinning spacecraft. So you will see also in Foresail 1, we are a bit, let's say, specialized in spin-stabilized spacecraft here, in comparison to like 3-axis stabilized spacecraft. And so the idea is we have to have a spin rotation, and then because this the field of view of the particle telescope, they want to scan the sky, and that's why we need a spinning kind of approach. So we run a bit the analysis, and basically this is the design we ended up with, sort of a 6U satellite with its wings opened up to the sun, and then rotating around this axis. And with a magnetic boom to isolate the magnetometer from interference of the actual satellite. And this is also something which comes up in the next slides, at some point with the magnetic interference. So I talked already about our orbit, and that it goes through the Van Allen belt, and here's actually the simulated situation. So this is the 2 Van Allen belts, and this is our orbit. The arrow is our orbit, and as you can see, we're actually all the time almost inside the orbit, inside the Van Allen belt, meaning the sheer amount of particles impinging on this mission is like high energetic particles is crazy. Meaning you have to not only think about total ionizing dose, which is like the accumulated dose, but also about high energy particles that create offsets and like single event effects in this case. And that's why I think if you want to run like a 10-year mission, for example, the cluster mission or a Van Allen probe, that's why they chose a more rugged approach, because if you have to endure so many single event upsets and like the total dose in general, you need to, like for more than like say 6 months or a year, you have to just build it more beefy and more like, basically you need mass, and you will see also later what we did. Right. One of the studies we did is like how much. So because the problem is, if we would just launch the satellite that you have seen like Foresail, Foresail 1, for example, or any other structure with like open holes in it, if you launch that, basically it's impossible because you're around here, so no shielding almost. Yeah, meaning you get a total dose of like almost infinite. Yeah, it's not infinite, but like 10,000s of kilograms, which is crazy. Yeah, or even megagrams in a single day. We don't need to talk about that. This kills almost all the electronics that are commercially available. Okay, so then we thought, okay, how much shielding would we need to employ around the whole satellite to actually achieve a level around 10 kilowatts over 6 months, 1 year, whatever. And this is this black bar here, meaning at around 1.5 grams per square centimeter, which is roughly 6 millimeters of aluminium, we can ensure that the total ionizing dose at least is low enough. Of course, we can do nothing about the single event effects with pure shielding, because single event effect, like a 10 mega electron particle will just go through. That you cannot do anything there. And basically, what we also did is we did there's a really cool paper by Anton. Actually, he said that he's not here, but Anton made simulations about different shielding materials on top of each other. Yeah. Up to like 5 layers of different materials. And what we found out are 2 things. First of all, it is only marginally better to go to a 3-layer approach than a 2-layer approach, and everything above 3-layer is basically bullshit. Because the gains that you're getting are in the per mil, and you're like the effort to get like the sandwich together is just bullshit. Like, so that's why you see here only 2 materials. Yeah. So we have aluminium and we have polyethylene. So basically just normal plastic in a sense, or some kind of plastic. And what you can see is the blue curve is aluminium on top of polyethylene. The orange curve is polyethylene on top of aluminium, meaning you can clearly see that the polyethylene above the aluminum will give you a lower dose, and that's also very important, that the stacking of the materials makes a difference. Okay, good. All right, then we talked about shielding. Okay, so basically we need to ensure that everything that we want to shield and every electronics component that is commercial off the shelf is shielded by 6 millimeters of aluminium. How do we do that? We just build a fucking tank. So we have basically 6 millimeter wall thickness everywhere. But okay, what the problem with a tank is, if I build it like this, how do I get through the wall when I need like electric connections to my magnetometer, my solar panels, my other sensors outside? So we need to think of like a solution of how to get, without risking the radiation to get into the actual structure. And what we have thought of is this kind of structure where you have like basically like an interconnecting connector in between. And here you have to make sure that every part, that's why this is also longer, for example, that every part is, so basically you can think of this like a light-tight box, because you want to make sure that there's no gap where a tiny bit of light can go through, right? And that's why you see this staggered design. So you have always this kind of labyrinth that you make for the radiation. And the cool thing, however, is that that we have shown in our simulations that PCB, like FR4 material, is equivalent, almost equivalent in terms of thickness to aluminium. Meaning you can use either 6 millimeters of FR4, assuming you don't have like vias or something like that, of course, or aluminium. That's why you see this as a green PCB, because this is way easier to manufacture, and it also provides you electrical connection for the connectors. So it's quite a smart idea, in my opinion. Also, so my idea, so I'm okay. So then the next thing. is, of course, we are going far away from Earth. We are going to like 45,000 kilometers away from Earth, meaning we have to think of our communications, right? Because it's not anymore that easy that you just calculate with 2,000 kilometers as a maximum, and that's it, and you have your normal LEO operations, and basically you don't you just almost have signal, yeah, and it's really not a problem. But here, the free path loss is devastating if you don't do anything about it. So, meaning we need some kind of a solution of, first of all, also the visibility with our orbit, because we want to be relatively close to the equator with our orbit, is relatively poor from Finland. This would be the visibility from Finland. You can see this is like, well, not too much existing. So there needs to be two strategies. One strategy is we in this mission we need to have some kind of ground station network that we can utilize, preferably at the equator, because they have the best visibility. And then of course we need to optimize our overpass time. So there's two concepts. Either we do a constantly sort of shouting kind of mode where every ground station is just constantly receiving, or we have, let's say, a 2-hour window or something like that where we downlink. The good thing, in a sense, about this orbit is the apogee is super stable. Like it's far away. That's true. But like the position on the sky is crazily stable because it's just so slow, right? The satellite. So in that sense, for like communications, linking something down at the apogee would be great, because you don't deal with Doppler shift or almost no Doppler shift. And the problem is, if you go to the perigee, Doppler shift is crazy because it's a lot faster than in a normal LEO situation. So maybe then, I don't know if you want to shortly say something about the S-band solution that we have and sort of figured out for this kind of a purpose.
Well, the main idea is that we just make a very low data rate for the S-band, and then that causes problem for communication protocols and in practicality if you want to keep breaks and so on. So that's why we're designing full duplex, which is, since we're also limited in space due to radiation shielding and so on, that's a real challenge to get it in a very small form factor, the full duplex, and to have a quite high transmission power. We are looking at 35 ppm and also extremely high efficiency inside the line. So we don't want, for example, traditional solutions have to use these different kind of data vectors, but those result in losses. So achieving this full duplex, high efficiency, it's quite difficult. And I didn't have a presentation prepared, but I can show you some stuff later on that will happen there.
That'd be awesome.
And here, this is one of the simulations. When we consider a ground station network of like some of the, so this was done with the Corbis collaboration in mind because they have the same problem. And basically, the ground stations that you can see here are those that I know that are part of the Corbis collaboration. And as you can see, like there is, especially at the apogee again, a cool, really good window to get actually things down.
That source is max R.
Okay. By the way, please interrupt me anytime. I'm not a lecturer.
I was just curious how that simulation was done. I was looking at the credits and I saw a company that we've been working with back home, and so it was interesting to see. But I was just curious.
Yeah, actually, this is done with the horrible tool, in my opinion. With
This is MATLAB, right?
Yeah, MATLAB.
This is MATLAB. Sorry. Then it was not done in. I thought it was done in. Yeah, exactly. But this was MATLAB. Okay, cool. Because I thought it was done in this horrible SDK. Yeah.
SDK is not horrible.
SDK is horrible. Shut up. No, but SDK is horrible because they have to pay for every shit that you want to simulate. Like I don't want to, like the basic SDK that we have is horrible. Let's call it that way. Okay, because I cannot even estimate my proper power budget with it. So yeah. Sorry. Small rant over. All right, now on to the payloads. So we are lucky enough that we have in Europe quite a nice like sort of building of like magnetometers. So there's two sort of magnetometer institutes that are really renowned and like that fly also on US missions and so on. One is the Imperial College London, and the other one is the IWF from Austria. And they are building like flux gate magnetometers, and we are lucky enough that they wanted to sort of, they had like this humongous thing lying around that they usually use for like bigger missions. And they saw the opportunity with us to develop a miniaturized version that is capable for CubeSat use. And what you can also see is that we left this part completely untouched. So the sensor itself it fits actually in the tuna can size, which is pretty cool. And what they then did over the last 3 years is miniaturize their electronics, and I can tell you this has been working really nicely. We had a really nice tests. We had interface tests which worked perfectly. We had deployment tests of the boom that you can see later on that worked also nicely. Unfortunately, so this is old version. I will not talk too much about this, but these images are bullshit. Okay, we are working on a way better. I can show you in the lab. Maybe I don't know if you have shown them already, but like we have a nice version of this. Okay. But the point is, so we're also not doing additive manufacturing anymore because why? There's no need for it in this case. Like it's just complicated design. That's why it wasn't good. Yeah? We simplified the design by now. The cool thing now is we are probably around lower than 300 grams just for the boom, which is pretty cool. And the very cool is that we are even exceeding our target of 50 centimeter separation. So we think that we can do 64 centimeter separation, which brings down the magnetic noise by a factor of more than 10 actually. So it's pretty nice to achieve that. Then we have Redbe, which is in a sense sort of a successor to this instrument. This instrument is an old version of the instrument that flies on Foresail 1. Or this is actually the instrument that was on Foresail 1. The Foresail 1 Prime looks a bit different. And here, this is a particle detector which has a scintillating crystal inside, and then it has just normal silicon detectors in the front and in the back to do basically vetoing different angles and also getting a path, a track of the particle. Because the problem is, if you go with too high energies, the particle will just fly through your detector. And then you can almost not sort of measure the energy loss. And the energy loss is what you actually need to determine what kind of particle was it. So that's why you need the track information, and then for lower energy particles, they are actually stopped inside the silicon detector in the scintillating material, and then the scintillating material creates light, and then you can just detect light coming out of the detector. Okay, and the light. The amount of light that is created is also proportional to the energy deposited into the material. I'm sorry, this was the physics excursion. This was my other background in my master's, so...
I've seen some of this before.
So okay, cool. So please ask anything. Then we have the Coulomb-Drake experiment. You will see this also in Foresail 1 and also in, if you look at the Estonian satellites, they also have it, because there's a close collaboration between sort of this area between like Estonia, Finland, and the Finnish Meteorological Institute. Because this technology has been envisioned by Pekka Janonen in 2004, and it is like physically proven or like theoretically proven that it works. So the idea is that you use a very thin tether, you reel that out. You apply high voltage, and then you sort of sail inside the solar wind. That's the idea. And the cool thing is this kind of technology you can also employ around Earth, but then you're not sailing in the solar wind, but you're using the Earth plasma to sort of either speed up your orbit velocity or brake your or like brake inside the orbit. That meaning you can sort of shorten your orbital lifetime with this. So that would be the unique deorbiting device, which is kind of cool because it requires no fuel other than electricity, which is anyhow you need on a satellite. So that's the idea. In Foresail 2, the idea is that you reel out a 300-meter long tether, and in the lab you see a piece of the tether. It's really hair thin, and it's 3 strands woven into each other, so that this has also resilience. So if it's cut on one strand, it will still hold the whole tether. Okay.
Are you working with Aurora at all? Because they are doing.
Yes, I mean no. I mean so the Pekka Janonen is also the founder, one of the founders of Aurora Propulsion, and basically this is just another track to get this technology verified. Okay. They started maybe a bit early with the spin-off, without like the actual sort of proof that it works actually. I mean, of course it works theoretically, but like it has not been.
The first attempt to bring this one to space was with SQ1, launched in 2014. Next one was with Aldo-1, our satellite, 2017, launched, and Aurora Propulsion was founded somewhere 2019-ish, I guess.
Yeah, and then Aurora Sat 1 was also what they tried.
Yes,
which
Aurora
was
Sat 1
in
was launched, I think, 22.
1, 2, something like that. Yeah.
1, 2, and unfortunately, because the platform failed, they were not able to demonstrate.
And then S-Cube 1.
2.
S-Cube 2 was also launched last year, but they had the problem that they were not released out of the deployer, which is pretty sad because, so they burned up in the atmosphere.
And SG1 and Alpha-1 in both cases was basically the same model, and it was launched, satellite was operating successfully, but they didn't manage to open the tether. They spun up the satellite, but they didn't manage to open. They released the launch, but the tether didn't deploy. And I think the assumption is that the motor had failed, or there was some kind of bump due to vibration that they didn't manage to deploy because of that. And these had been fixed for SG2 and Foresail 1, but the different challenges have arisen.
So basically, at this state, unfortunately, all the attempts were either negated by the platform or by payload issues. Right, then we have an internal development. I'm sorry, this is also old material that I'm showing here, but sadly Anton isn't here. There's also a new prototype for this. So what we want to try here, so Anton has done, as I told you, this kind of real cool simulations about the different layer structures. And what we basically want to do then is, you saw this bathtub curve, this one on that side. And Anton wants to verify for different materials and different material combinations these kind of curves, because at the moment it's based on like a physics model. It's a GR4 model that they also use in CERN and so on. So it is based on theory, but like all the measurements have not been done yet fully. So the idea is that with this experiment we have different material combinations in like disc shape, and underneath we just have a normal radiation sensor, and then we just measure. Okay? And then these here are control measurements that we want to do. So basically different thicknesses of aluminium, and then we can basically see the aluminium bathtub shape also precisely, and also we know sort of more precisely for each thickness how it looks like. So that's the idea there. So let's see what I have done. Yeah. Before we come to the actual satellite design, because this is a very complex mission for, at least for us, it's the first step towards a 6U mission. It's the first step towards a sort of very complicated science mission, actually, in collaboration also with, or the idea was in collaboration with multiple other satellites and so on. So that's why I sat down and because it was too much to like gather in and actually make a just a sketch or something like that of the mission. So what I did is I used a software called Capella with a model-based systems engineering approach. And basically, it's, in a sense, it's just a software where you put down diagrams and connections. I mean, it's not much else. You can do all of this also in other way, like Excel or whatever. But like this is how I found it to be quite nice. Basically, what you see here is the so okay, maybe before I go into this, Capella is using a method called Arcadia, and Arcadia goes from sort of different levels. So the first level is you define your mission capabilities, basically you say you have these actors, they want this and that from that mission. So basically, like it's a different way of defining requirements. Okay. And then once you have that, then you go into mission functions, basically. So what kind of functionality does the system that fulfills this kind of a mission needs to have in order to fulfill the goals? Okay, and then once you have that established, then you go into the actual like implementation, where you draw then these kind of things, for example, where you say, okay, this functionality is then in this system or this subsystem and connected with like the sort of the data comes from here and then it comes and goes somewhere else and so on. Sort of you build your black box system of systems with this sort of software. And then the cool thing is that they even have one more layer where you can even model the actual physical components where these different functionalities, different black boxes are situated. So, for example, it might be in the Foresail 1 case, for example, the ADCS system is situated in the same physical component as the OBDH system, as the onboard data handling and control system. Okay? Right, so what you see here, I'm sorry that it's a bit small, but basically you have here is the platforms teams, that's us. Then here is the Alto ground station, and here are ground station providers. The Alto ground station is primarily used for sending like commands up to the spacecraft, and the ground station providers are mainly used for gathering the science data. And then basically what I did is like I made the sort of the data flow, so there's some commands coming there into the antenna. We have different antennas, like one patch antenna and two other dipole antennas. Then in the communication system, it will be processed, encoded, decoded, and so on. Then it goes to the OBDH, where you have it will just process the commands and select the correct system to send it to. And in this case, let's say we are going for the Coulomb drag experiment. It will sort of send the command to the Coulomb drag experiment. There, it will be processed and so on and so on. There will be an acknowledgement or some kind of thing sent back. This will be then sent to the storage unit on the OBDH, and then it goes back into the processing, into the communication system, and will be downlinked there. So this is the diagrams that you can make. There's tons of diagrams that you can make. I have like 100 or something like that of different kind of diagrams made with this software, which is really cool because the idea is that it is good for a conceptual phase, but it's also really cool if you keep them up to date. You can print them out, and then you can do, once the satellite is in orbit, an error analysis of like, okay, I know I have received a wrong command here, or there's some error there. Then I know, aha, this is this link. So what can I do about this link? Who are the actors? Who are the physical components, maybe even related to this link? What is the problem here? So this is also a very nice way of like looking forward already, like forward, basically future documentation in a sense, or forward documentation of missions. Yeah, maybe I should have clicked further. Sorry. Right. Okay, and then as you have already seen this stuff, we are, and I also explained to you already that we are very much building our own hardware in Aalto. So that's also why you're here, basically. So we have developed our own stack. We have developed a digital sound sensor and an analog sound sensor, and we are actually currently in development of a new analog sound sensor, which is it sits somewhere in between those. Because the problem with this mission is also, if you think about the hardware that I cannot shield, that there's several hardware items that I just cannot shield because they have to be outside of the box. One hardware is solar panels. Well, they are fine actually. You can just slightly increase the cover glass thickness, and that's fine, and you just acknowledge that there's a higher degradation factor, and that you just scale up a bit the system, no problem. However, sun sensors, so your position, your attitude sensors is really much not so shielded, and actually a problem, because if you go the digital route, which is cool because you can do like you can differentiate between like the sun and the moon and stuff like that, they will die almost instantly, because like the chip on there is like just dead basically. Because it's like it receives megahertz, it's like insane. Forget it. Then you have to go the old school way of like analog sun sensors. But even they get like 10 megahertz or even more during the mission lifetime. So you have to think of like, how do I make a more redundant system, let's say, or and how do I test my system? And it's actually what we did in December. We had one of our new prototypes in a beam where we basically reached the maximum that we can reach in this kind of a facility with this amount of time, which was 600 kilorats onto the actual sensor. And there was a small degradation, but it was within the limits that we have set ourselves, so this is quite promising in that sense. And then the problem, as you can see here, is this kind of sensor has the onboard electronics on the actual sensor. Of course, this I could not fly in my Foresail 2 mission, but I can fly it if I separate the actual sensor from the processing part, because the processing part I can put then into the tank again. Okay. And I think where we are very proud of actually is that we built our own solar panels. Because solar panel manufacturing, I mean, of course we don't build our own cells, but solar panel manufacturing is something that most of the teams don't